quantum entanglement. It's not just a sci-fi trope.
Yeah.
You know, this stuff is real.
Although it's definitely real.
And it's poised to completely revolutionize computing as we know it.
It's true. We're talking about particles linked across potentially vast distances, where the act of measuring one instantly reveals the state of the other. It's like they're communicating faster than the speed of light, something that baffled even Einstein.
Yeah, I've read a bit about this spooky action at a distance, as Einstein famously called it. But honestly, it still feels like something out of Star Trek. How do we even know this isn't just some theoretical quirk? And how does it actually work in the real world, specifically in quantum computers?
Well, it's definitely not just theoretical. In fact, the violation of something called Bell's inequalities has experimentally proven the non-local nature of entanglement. It's one of the most mind-blowing discoveries of the 20th century.
Bell's inequalities. I've heard that term, but to be honest, I'm a little fuzzy on the details.
Imagine you have two coins and you flip them simultaneously. Classically, the outcome of one flip wouldn't affect the other. But with entangled particles, it's as if the coins are linked. If one lands heads, the other instantly lands tails, no matter how far apart they are. Bell's theorem sets up a mathematical test to see if this spooky correlation is stronger than what classical physics would allow. And guess what? It is.
So these experiments are actually showing that the outcome of measuring one particle can instantly influence the state of the other, even if they're light years apart. That seems to defy everything we know about cause and effect.
It does seem that way, doesn't it? It's one of the many mysteries that quantum entanglement presents us with. But here's where it gets even more interesting. This phenomenon is not just a scientific curiosity. It's the driving force behind the potential of quantum computers.
Okay, so we've established that this isn't just theoretical, and that it's more than just a weird quirk of the universe. But how does it actually translate into the power of quantum computing? What makes these entangled particles so special in that context?
Think of it this way. In a typical computer, information is stored in bits, which can be either a 0 or a 1. But in a quantum computer, we use qubits, which can be in a superposition, both 0 and 1 simultaneously. It's like a coin spinning in the air, being both heads and tails at the same time, until you force it to land and choose a side.
Right. I remember that from our previous deep dive into quantum computing. Qubits are like the quantum version of bits, with this amazing ability to be in multiple states at once. But how does entanglement play into this?
Well, entanglement is what allows us to link these qubits together, creating powerful correlations between their states. When you measure one entangled qubit, you instantly know the state of its partner no matter how far apart they are. This ability to manipulate and measure entangled qubits is what gives quantum computers their incredible computational power.
So it's not just about the individual qubits being in superposition, it's the entanglement that connects them and allows them to work together in a way that classical bits can't.
Exactly. It's this interconnectedness that allows quantum computers to tackle certain types of problems that would take classical computers billions of years to solve.
That's incredible. So we have these qubits in superposition, entangled together like tiny coordinated dancers. But how do we actually create this entanglement in the first place? Is it something that just happens naturally? Or do we have to force it somehow?
It's not something that typically occurs naturally. We have to engineer it using specific tools called quantum gates. You can think of them like logic gates in a classical computer, but instead of manipulating bits, they manipulate qubits.
Okay, so quantum gates are like the tools we use to choreograph this intricate dance of entangled qubits. Can you give us an example of how one of these gates actually creates entanglement?
Sure. One common method uses a gate called a CNOT gate, which stands for controlled NOT. Imagine you have two qubits. One is the control qubit, and the other is the target qubit.
Got it. One's calling the shots, and the other's following directions.
Right. Now, if the control qubit is in the state 1, it flips the state of the target qubit. If it's in the state 0, it does nothing. The key is to apply the CNOT gate when both qubits are in a superposition, that fuzzy, both states at once world.
So it's like the control qubit is saying, if I land on heads, you flip to tails, but if I land on tails, you stay the same. But since they're both in superposition, it's like they're exploring both possibilities simultaneously. And that's what creates the entanglement.
That's a great way to visualize it. And once we have these entangled qubits, we can use them for all sorts of amazing things, from unbreakable codes to teleporting quantum information.
Okay, now you've got me really intrigued. Let's dive into those applications next. What's the so what of entanglement? Why should we care about these spooky linked particles? So we ended part one talking about quantum gates being used to create entanglements, like we're choreographing this intricate dance of qubits.
Yeah.
But now I'm really curious about these applications you mentioned. Let's start with unbreakable codes. How does entanglement actually make that possible?
It all comes down to the fact that any attempt to eavesdrop on entangled particles will inevitably disrupt their delicate connection. Imagine you and I want to share a secret message.
Okay, let's say we do.
We could each receive one particle from a pair of entangled particles. Now, because they are linked, if someone tries to intercept your particle to steal information, the entanglement breaks down, we would immediately know that something's fishy.
So it's like a built-in alarm system.
Yeah.
That's really clever. It seems like this could completely change the landscape of cybersecurity. No more worrying about hackers cracking our encryption.
Exactly. It's called quantum cryptography, and it holds the potential for virtually unbreakable communication. It's one of the most promising applications of entanglement.
That's amazing. What else can we do with these entangled particles? You mentioned something about teleporting quantum information.
Ah, yes. Quantum teleportation. It sounds like science fiction, but it's a real phenomenon. Now, we're not beaming people across space like in Star Trek, at least not yet.
Okay, so no teleporting humans just yet. What are we teleporting then?
What we can teleport is the quantum state of a particle. It's like sending a blueprint of the particle's information to another location, allowing it to be reconstructed there, without physically moving the particle itself.
So instead of sending a physical letter, we're sending instructions on how to recreate the letter at the destination. That's incredible. But how does entanglement make this possible?
We use entanglement to create a channel, a special connection, between the original particle and a particle at the destination. Through a series of measurements and classical communication, we transfer the information about the original particle's state. It's then reconstructed at the destination, effectively teleporting its quantum state.
It's like sending a recipe for a cake, and then someone at the destination uses those instructions to bake an identical cake. Except we're talking about quantum states instead of cake ingredients.
That's a delicious analogy. It highlights the fact that we're not transmitting the physical particle itself, just the information that defines its quantum state.
So we've got unbreakable codes and teleportation. What other advantages does entanglement bring to the table, particularly in the context of quantum computing?
Well, one of the most significant advantages is the ability to perform parallel processing on a scale unimaginable with classical computers. Imagine a classical computer as a single chef, trying to cook one dish at a time. A quantum computer, thanks to entanglement, is like having a whole team of chefs working simultaneously on different parts of the meal. They can explore many different possibilities at once, drastically speeding up the cooking process, so to speak.
So it's like instead of trying every recipe one by one, a quantum computer can explore all possible recipes simultaneously. That's an incredible speed advantage.
Exactly. And remember how qubits can be in a superposition, representing both 0 and 1 at the same time. This means that a system of entangled qubits can embody an enormous number of states simultaneously, exponentially more than the same number of classical bits. This ability to explore multiple possibilities at once is what gives quantum computers the potential to outperform classical computers. For certain types of problems,
it's mind-boggling to think that we can harness this strange quantum phenomenon to perform computations in a completely new way. It's like unlocking a hidden dimension of computing power.
It is. This potential for massive parallelism opens up exciting possibilities for tackling complex problems in fields like medicine, material science, and artificial intelligence.
It all sounds incredibly promising. But if I'm being honest, there's a part of me that wonders, if this entanglement is so delicate and sensitive, how do we even maintain it in the real world? Isn't it incredibly fragile?
You're right to be skeptical. One of the biggest challenges in quantum computing is maintaining the delicate balance of entanglement. There's this constant battle against a phenomenon called decoherence.
Decoherence, what's that?
It's the tendency for quantum systems to lose their coherence, their delicate quantum properties, due to interactions with the environment. Think of it as noise or disturbances from the outside world that disrupt the entanglement. It's like trying to choreograph a delicate dance in a room full of rowdy kids. The slightest bump or jostle can throw everything off.
So it's like the entanglement fades away or gets scrambled because of all this outside interference.
Precisely. And this decoherence is one of the main reasons why we haven't yet built large-scale, fault-tolerant quantum computers. It's incredibly difficult to shield these delicate entangled states from the noisy environment.
It sounds like a real challenge.
Yeah.
But I'm assuming researchers are working hard to find ways to overcome this hurdle.
Absolutely. There are many brilliant minds focused on developing techniques to mitigate decoherence. It's like trying to build a soundproof, temperature-controlled, vibration-free room for our entangled qubits to dance in undisturbed. Some of the approaches include using error correction codes, developing more robust types of qubits, and exploring ways to shield qubits from environmental noise.
It sounds like a constant race against time, trying to harness the power of entanglement before decoherence sets in and washes it away.
It is a race in a sense, but despite the challenges, progress is being made every day, and the potential rewards are so enormous that it's a race worth running.
I'm starting to grasp the incredible power of entanglement. But I'd love to understand a bit more about the mathematical framework behind it. I know we've been using a lot of analogies, but I'm sure there's some serious math involved, right?
Absolutely. The math is essential for describing and predicting how these entangled systems behave. It's a fascinating area, but it can get pretty complex.
I'm up for a challenge. Can you give us a taste of how mathematicians describe entanglement without getting too lost in the equations?
Sure. So one of the key mathematical concepts is something called a wave function. It's a mathematical description of a quantum state. And it basically tells you everything you can possibly know about a system.
So it's like a blueprint that contains all the information about the particle's state.
Exactly. And these wave functions live in a special kind of mathematical space called Hilbert space.
Hilbert space. It sounds like something out of a science fiction novel. What is it exactly?
Think of it as a multidimensional space, kind of like a coordinate system, but one that can handle all the weirdness of quantum mechanics. It's the mathematical stage where these quantum states and their entanglements play out.
Okay, so it's a mathematical framework that allows us to make sense of these bizarre quantum phenomena.
That's a great way to put it. And the beauty of this mathematical framework is that it allows us to make precise predictions about how entangled systems will behave. It helps us understand the probabilities of different outcomes when we measure these entangled particles.
So it's not just about describing entanglement in a qualitative way. We can actually calculate and predict its spookiness using these mathematical tools.
Exactly. And one of the most important mathematical results related to entanglement is something called Bell's theorem, which you brought up earlier. It provides a way to test whether the weirdness of entanglement is real or just an artifact of our incomplete understanding of quantum mechanics.
Right. You mentioned Bell's inequalities before. Can you remind me how that works again?
Imagine you have a theory that tries to explain the correlations we see in entangled particles using hidden variables. These hidden variables would be like secret instructions carried by the particles, determining how they will behave when measured. Bell's theorem says that if such hidden variables exist, then certain statistical correlations between measurements on the entangled particles must be limited. They can't be stronger than a certain value.
So it's like setting a speed limit for how strong these correlations can be if they're based on some kind of local, hidden information.
That's a good analogy, but here's the mind-blowing part. Experiments have consistently shown that the correlations in entangled systems violate these Bell inequalities. They exceed the speed limit.
So that means those hidden variable theories are wrong.
Yeah.
There are no secret instructions.
That's right. The violation of Bell's inequalities is one of the strongest pieces of evidence we have, that the world is truly quantum, and that the spookiness of entanglement is an inherent feature of reality.
That's incredible. So we have this powerful mathematical framework to describe entanglement and experimental proof that it's real and weirder than we could have imagined. Where do we go from here? What are some of the frontiers of research in this field?
Well, there are many fascinating directions that research is taking us. For instance, we're starting to delve into even more complex aspects of entanglement, like density matrices, which are used to represent mixed states, those that are not perfectly pure and isolated.
So more like the messy real-world entanglement we're likely to encounter in practical applications.
Exactly. And there are also different ways to quantify the amount of entanglement in a system, like von Neumann entropy and concurrence. These measures help us understand the strength and quality of entanglement, which is crucial for designing and building reliable quantum computers.
It sounds like the deeper we go, the more intriguing it gets. But I'm curious, what about the actual hardware? I mean, all this talk about qubits and entanglement is fascinating. But how do we actually build these quantum computers in the real world? What are the different platforms being explored?
That's a great question. It's a whole other deep dive in itself. But to give you a taste, there are several promising approaches, each with its own advantages and challenges.
Okay, let's hear about them. What are some of the leading contenders in the race to build a quantum computer?
One of the most well-established platforms uses superconducting qubits. These qubits rely on superconductivity, a phenomenon where certain materials, when cooled down to extremely low temperatures, conduct electricity with zero resistance.
Superconductivity. That sounds pretty super already.
It is quite remarkable. These superconducting materials allow us to create tiny circuits that act as qubits. By carefully controlling these circuits, we can manipulate and entangle the qubits.
So it's like building a miniature, ultra-cold playground for qubits to dance in.
That's a good way to visualize it. However, superconducting qubits are very sensitive to noise and decoherence, so they require careful shielding and control to maintain their delicate quantum states.
So it's back to that battle against decoherence again. What other platforms are researchers exploring?
Another promising platform uses trapped ions, which are individual atoms that have had some of their electrons stripped away, giving them a net electrical charge.
So instead of using circuits, we're using actual atoms as qubits.
Exactly. These ions are held in place, or trapped, using electromagnetic fields. We can then manipulate their quantum states using lasers, which is quite fascinating.
It sounds like a delicate high-tech dance. Trapping these ions and controlling them with lasers. What are the advantages of this approach?
One of the biggest advantages is that trapped ions are very well isolated from the environment, making them less susceptible to decoherence. However, the challenge lies in scaling up this technology to create large numbers of entangled qubits. It's a delicate process that requires extreme precision.
It seems like every approach has its own set of hurdles. Are there any other platforms worth mentioning?
Definitely. There are also photonic systems, which use photons, the particles of light, as qubits. Photons are amazing because they can carry information over long distances and are relatively immune to decoherence.
So light itself could be the key to building robust quantum computers.
That's fascinating. But I imagine there must be challenges with this approach, too.
Of course. The biggest challenge is building optical circuits that can manipulate and entangle photons in a reliable and controlled way. It requires incredibly precise engineering at the nanoscale.
It's amazing to see the creativity and ingenuity that's going into building these quantum computers. It's like we're pushing the boundaries of what's technologically possible.
It's a truly exciting time to be involved in this field. We've only just begun to explore the potential of quantum computing, and the future holds incredible promise.
Well, before we get too carried away with the future, I think we need to take a moment to let all this information sink in. We've covered a lot of ground, from the basic principles of entanglement to the challenges and potential applications.
Indeed. We've journeyed through the theoretical foundations, the experimental evidence, and the engineering marvels that are shaping the future of quantum computing. But the story doesn't end here. We've still got a lot more to explore, including the future of entanglement and its impact on the world.
That's right. Join us in part 3 as we delve into the cutting-edge research that's pushing the boundaries of what's possible with entanglement. We'll be exploring concepts like topological quantum computing, quantum networks, and the mind-boggling possibilities they hold.
Welcome back to our deep dive into the fascinating world of quantum entanglement. We've covered a lot of ground, from the fundamental weirdness of entangled particles to the challenges and potential of building quantum computers. But now I'm really excited to explore the future of this field. What's on the horizon? What are the next big breakthroughs that entanglement might enable?
It's an exciting time to be exploring these questions. One area that's generating a lot of buzz is topological quantum computing. It's a completely different approach to building quantum computers, one that leverages the unique properties of exotic states of matter.
Exotic states of matter. That sounds intriguing, but also a bit intimidating. Can you break it down for us?
Imagine a world where particles can behave in ways that defy our everyday intuition. These exotic states of matter, called topological phases, host quasi-particles called anyons. Unlike the particles we're familiar with, anyons have some very peculiar properties.
Okay, so anyons are like the rule breakers of the quantum world. What makes them so special?
One of their most fascinating characteristics is that they remember their braiding history. Imagine braiding strands of hair. The order in which you cross the strands affects the final pattern. Similarly, the way anyons are exchanged or moved around each other leaves a unique imprint on their quantum state.
So it's like their movement creates a kind of quantum memory.
That's a great analogy. This braiding history can be used to encode and manipulate quantum information in a way that's inherently protected from decoherence.
Wait, so topological quantum computing could be the key to solving the decoherence problem. That's a game changer.
It has the potential to be. By encoding information in the topology of these anyonic systems, we could create quantum computers that are much more robust and resistant to the environmental noise. That causes decoherence.
It's incredible to think that the solution to one of the biggest challenges in quantum computing might lie in these strange, almost abstract topological phases. But if this approach is so promising, why aren't we building all our quantum computers this way right now?
There's a catch, of course. Creating and controlling these topological phases in the lab is incredibly challenging. It requires extremely precise conditions, specialized materials, and a deep understanding of condensed matter physics.
So it's still early days for topological quantum computing.
It is. But the potential payoff is so significant that researchers are pouring immense effort into overcoming these challenges. If we can crack the code of topological quantum computing, it could revolutionize the field and lead to incredibly powerful and reliable quantum computers.
It's exciting to think about the possibilities. But let's shift gears a bit. You also mentioned something about quantum networks earlier. What are those, and how do they relate to entanglement?
Quantum networks are another mind-boggling concept, with the potential to transform the way we communicate and compute. Imagine a world where we can connect multiple quantum computers together, forming a kind of quantum internet.
A quantum internet, that sounds like something straight out of science fiction. What would that even look like? And what could we do with it?
It would be unlike anything we've ever seen before. It would allow us to share and distribute quantum information across vast distances, enabling applications like ultra-secure communication and distributed quantum computing.
So instead of being limited to the power of a single quantum computer, we could have multiple quantum computers working together on a problem, like a giant interconnected quantum brain.
That's the idea. And the key to building these quantum networks, as you might have guessed, is entanglement. We need ways to generate and distribute entangled particles over long distances, connecting different nodes in the network.
So entanglement is not just the heart of quantum computers, but also the glue that could bind them together into a global quantum network. That's pretty mind-blowing.
It is, and as we continue to explore and understand entanglement, we're likely to discover even more amazing applications and possibilities that we haven't even dreamed of yet.
This whole deep dive has been a wild ride. We started with this seemingly bizarre concept of entangled particles, and now we're talking about teleporting quantum information, building computers based on exotic states of matter, and even creating a quantum internet.
It's been a journey through some of the most mind-bending concepts in physics, but hopefully we've shown that it's not just about abstract theories. Entanglement is a real phenomenon with the potential to transform our world.
I think our listeners are probably feeling a bit overwhelmed with information right now, but in a good way, of course. It's a lot to absorb. But before we wrap up, I want to bring it back to the big picture. Why should our listener care about entanglement and the future of quantum computing?
Well, for one thing, it's a testament to the power of human curiosity and ingenuity. We're exploring the fundamental nature of reality and discovering things that challenge our deepest intuitions about the universe.
It's like we're rewriting the rules of the game. But beyond the scientific implications, what about the practical side? How will this impact people's lives?
Quantum computing has the potential to revolutionize countless industries, from medicine to finance to material science. It could lead to breakthroughs in drug discovery, personalized medicine, the development of new materials, and a deeper understanding of the universe itself.
So it's not just about building faster computers, it's about tackling some of the biggest challenges facing humanity and unlocking new possibilities that we can barely imagine right now.
Exactly, and entanglement will undoubtedly play a central role in this unfolding quantum revolution.
Well said. I think it's time to leave our listener with a final thought, something to ponder as they continue their own exploration of this fascinating field. What do you think?
Here's something to consider. We've talked about teleporting quantum information, but could we one day use entanglement to teleport physical objects as well? It's a question that pushes the boundaries of what we currently believe is possible and invites us to imagine a future where the lines between science fiction and reality become increasingly blurred.
That's a perfect note to end on. A quantum that captures the wonder, the potential, and the almost limitless possibilities of entanglement. Thanks for joining us on this deep dive into the quantum world.
It's been my pleasure. Until next time, keep exploring, keep questioning, and keep wondering. The quantum future is full of surprises.